So let me review a little bit where we were last time. All right, we were talking about a subject called statistical mechanics. And we started off with the idea that if you have a closed system, so here's my system, it's closed, isolated, then we can imagine that the particles in that closed, isolated system can exist in many, many different arrangements or microstates or configurations. Those words are sometimes used interchangeably. So I gave the analogy, the particular places where you're sitting is an example of one microstate. And if you move, even one of you moved, that would be a different microstate. So the connection between thermodynamics and statistical mechanics comes from this formula. The entropy, S, so this is the entropy, is equal to Boltzmann's constant K times the log of the number of microstates there are. So this is a number of microstates. And in this case, they all have the same energy, the same volume, and there's the same number of particles. So that's the starting point for all of statistical mechanics. And from that, you can derive everything else. And I'm going to show you, I'm not going to do most of the derivations, but I'm going to write down one of the most important results that's derived in the notes. OK. But before I do that, let me indicate one important feature of this situation. In this situation, the probability of being in any particular microstate, any one particular one, is the same for all microstates in this case. So if I say P sub I, that's equal to 1 over omega. And since omega is just one big number, it's the same for every microstate. So this is the probability of being in the ith microstate. And all of them are the same. So the probability of you sitting here like this is the same as if you moved over here. All right? Or you moved up there, or any other combination. Now, of course, that's not really true in this classroom. Why is that not true? Because, yeah, you sit next to your friends, you do other things. There's more people sitting up front here, which is nice. So there's constraints on the system that determine how the microstates are. But in the statistical mechanics case, for liquids, gases, solids, things like that, there's, for a particular energy, we assume every microstate has the same probability if the system is isolated and closed. No interactions with the outside world. And that's what you always do in probability theory. When you have no idea what the probabilities are, you assume they're all equal. But now we're going to look at a slightly different situation. Rather than an isolated system, we're going to look at a system that is connected thermally. So here's my system. It can exchange energy with some huge heat bath that's at some temperature T. So the temperature of the heat bath, this is called a heat bath or a reservoir, and this is called the system. So we call this a heat bath or a reservoir. So energy can flow in and out of the system, thermally connected. But the system's volume is constant, and the number of particles is constant. So what's an example? An example is this piece of chalk. it can exchange energy with the air. There's nothing stopping it from doing that. But the number of particles in this chalk is constant, except when I write on the blackboard, right? But usually it's constant. And its volume is constant. But it can exchange energy with the environment. And that's true for most of the situations here. It's true for you, it's true for your paper, for your pencil, all of that. So that's why this situation is more useful. It's not only more useful, more common, it's also easier, as you'll see in a minute, to actually derive some conclusions, some results. But in order to do that, I need to know what this is for this situation. And here's the answer. The answer is the probability is e to the minus e sub I over kt divided by z. And z is the sum over all the microstates of e to the minus e sub I over kt. Maybe I'll make this a j here. So this j is different than I. So in this case, the probabilities depend on the energy of the microstate. Each microstate has a different energy. So in this classroom, for this analogy, there's a model called a lattice gas model. And in the lattice gas model, if two particles are next to each other, they have an energy, an attractive energy, minus j, or minus epsilon, minus some number. There would be an energy associated with you two, because you're next to each other, but there's no energy associated with you two, because there's a vacancy between them. So that's an actual model in physics. It's a model of a liquid gas, a fluid. All right? And which microstate will occur if we put that model into a heat bath is given by this formula. This is called the partition function. And this probability is probably one of the most important results of all statistical mechanics. It's called the Boltzmann distribution. So Boltzmann did most of his work in the late 1800s. He literally was one of the first to realize and promote that matter was made of atoms and molecules. I don't know if he used those words, but that it was made of particles. Most people didn't think that. They looked at the air. I don't see any particles. Do you? Do you? Nobody sees any. Look at your table. Do you see any particles in there? No. Even though there were some Greek philosophers a couple thousand years before who had that idea that matter was made of particles. But by the 19th century, it wasn't clear. People didn't think that. All right. So what does this say? What does it mean? Well, one thing it means, because of this minus sign, the larger the energy, the lower the probability. Okay? So if I plotted P sub I versus E sub I, E, I get a plot that's exponentially down. Okay? So that's what P sub I is. But there's another probability you might be more also interested in. And that's the probability that the system has energy E. So this is the probability the system has energy E. All right? Notice that this is not the same as this. What's the difference? Well, the difference is the following. This is equal to omega V times pi of V. So what this pi of V means is all the this means the probability of being in the ith microstate which happens to have the energy E. This is the number of microstates with energy E. And what does that omega E looks like? What does this look like? Well, it's going to grow rapidly. It's going to look like that. So that's omega V. All right. You take the product of those two, and what you get is something that might look like this. All right? So this is omega V pi. So in other words, the product looks like what you might have heard of, a Gaussian distribution, a bell-shaped curve, things like that. And that is true. So in this piece of chalk, the probability that it has a certain energy is like that. It's very sharply peaked, though. Very sharply peaked. These diagrams don't really do justice to how sharp this bell-shaped curve is. It's very sharply peaked around a single energy, which you can't figure out unless you know how this depends on energy. Okay, and that's a complicated thing to do. Okay, so that's the key ideas. Now let's look at some applications. So imagine you have a molecule that's in a fluid. Like in chemistry, you might have a molecule in water. And that molecule can exist in two states, right? And that's typical, right? The molecule usually can consist in more than two, but maybe two are very important. There's a ground state, maybe an excited state. Or maybe there's two conformations of the molecule that are important. Sometimes you hear this cis state, a trans state. Maybe you've heard that in chemistry. All right, so let's consider that. So we're going to do applications here. Let's consider molecules in a fluid that has two important states. All right. So with that, I can figure out how many of those molecules will be in one state and how many will be in the other. How do I do that? I just use the Boltzmann distribution. Where is it? Right there. So I have n of 1 over n of 2. So this is the number of molecules in state 1, number of molecules in state 2. And the ratio will be e to the minus E1 over kt divided by e to the minus E2 over kt. Okay, I just take the ratios of the probability. And since z is a constant, that cancels out. I'm all done. So I can do that. You give me you put a bunch of molecules in a fluid, and those molecules, if they can each be in just two states, I can tell you how many will be in one compared to how many in the other, just like that. So that's one crucial, nice example. Or another one that's very similar to this. How many defects, and I'm going to put point defects, like a vacancy, are there in a crystal? Well, the answer is you just use the Boltzmann distribution. So this number will be proportional to, I'd have to work out what the proportionality constant is, e to the minus the energy of the defect over kt, where e equals the extra energy of the defect. So you see, this explains why at low temperatures you have fewer defects than at high temperatures. Now, I don't know the proportionality constant. I'd have to figure out, there has to be some way of putting that in. But if I did a plot and I measured how many defects there were as a function of temperature. If I did a log-log plot, I'd get a nice, not a log-log, semi-log plot, I get a nice straight line. So if I plot the log of n versus 1 over t, I would get a plot, a slope like that, and the slope would equal minus e over k. Why? Because if I take the log of n, I get minus e over kt. All right, so if I plot log n versus 1 over t, the slope is minus e over k. Okay, so you can do that. And there are many other experiments you could do. There are parts of the system or other pieces that are in a thermal connected to a heat bath where you want to know how much of that configuration or that energy state there will be. All right, now let's get back to some results that might be a little bit easier for you to understand because we've talked a lot about it. So I want to ask the question, what is the probability that a particle has a x component of its velocity, what's the probability that it has a particular value? So what I'm doing here is I'm imagining every particle as being like my system. But even more, I'm just imagining that I'm just treating the x component of the particle, x component of its velocity, as my system. Well, I just write down the Boltzmann distribution. All right, so the probability that a particle has a velocity component, let's call it the x velocity component, is the following. P, it depends on x, v sub x, is just equal to some constant e to the minus. So what's the energy associated with this component? Well, it's just kinetic energy. So I have 1/2 mvx squared divided by kt. All right? That's the probability. It's actually a probability density. If I really wanted to make it a probability, I have to have a small range of v sub x around which I want to do it. All right, so the way we usually do that is we put a little dvx here and a little dvx here. All right, so this is the probability of a particle having Vx between Vx and Vx plus dVx. All right, so it's just that probability. And I can figure out what A is. This equals square root of m over 2 pi kt e. It's 1/2 m Vx squared over kt dvx. And this comes from making it so that the integral from minus infinity to infinity of p of vx dvx is equal to 1. So that's how I figure out what A is. Now, you probably don't even know how to do that integral. I actually remember how to do it. You can look it up. I'm sure you can find it online. It's in a million places. All right? But that's where it comes from. All right. So what? Well, there's some really neat things we could do with that. All right? Let me give you an idea of what that means. Because now what I'm going to do is I'm going to connect statistical mechanics, this result right there, I'm going to connect that to some result that we got in the very beginning of our discussion of thermal physics. At the very beginning. I'm going to make a connection. All right. So what does that mean? Well, let's say I had a plot. This is a strange plot. I'm plotting Vx, Vy, Vz. All right? So what is this saying is that if I'm over here with a particular value, all right, I can't really do it very justice, but this is some particular Vx, Vy, Vz. It's not a point, it's a little patch. Okay, and I asked, what's the probability of having that being in that patch? Right? The particle could be anywhere on this graph because it could have a velocity anywhere. There's no velocity that is forbidden. They're all probable. But what if it's on this little patch here surrounding this point? What is that? Well, the answer is I just multiply this for PVX, PVY, PVZ times dx, dVx, dVy, dVz. That's the probability of being in this patch. Right? Well, it's the same for Vx, Vy, Vz. So it's just equal to m over 2 pi kt to the 3/2 times e to the minus 1/2 mv squared over kt. And then I have this dvx, dvy, dvz. All right, that's kind of neat. So now I know the probability not just of having one component being that, but all three being specified. How did I get from Vx squared and Vy squared, Vz squared to V squared? How did I get that? Did I do some really fancy advanced math to do that? From taking this and multiplying it by PVY, PVZ. How did I get this? So he said a triangle. Well, that's where Vx squared plus Vy squared plus Vz squared is equal to V squared, right? That's a generalization of the Pythagorean theorem, right? So you have V squared equals Vx squared plus Vy squared plus Vz squared. Good. But why did I add them when I'm multiplying exponentials? Why does that work? So if I have e to the a times e to the b, what does that equal? E to the a plus b. That's all it is. Okay, so it's not that hard. Now, I'm going to do something really neat. Okay, I'm going to ask the question, I don't care about the individual components. I want to know the probability that the particle has a certain speed, v. How do I figure that out? Because there's going to be many, many values of Vx, Vy, Vz that give you the same v. So how do I figure that out? Well, I imagine this patch here that's in a sphere. So this is a sphere. You have to give me, it's some kind of sphere, okay? And I'm looking at a little shell of that sphere. So this is a shell of sphere of radius, the speed v. And let's say it has a thickness, let's say there's a thickness dv for that shell. What's the volume of that shell? what's the volume of that shell? So it has a thickness dV. It's on a sphere of radius v. What is the volume of that shell? So the volume of this shell, so the volume equals 4 pi v squared dv. So I can replace all this with that. And so I get the following result. P of v is m over 2 pi kt. Oops, I want to put my little dv here. To the 3/2 e to the minus 1/2 m v squared over kt times 4 pi v squared dv. All right, so this defines P of v. It's just given by this. And this, believe it or not, is actually written down in your textbook. And it's called the Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution, speed distribution. Let's call it the speed distribution. All right, so it's telling you the probability of having a certain velocity, a certain speed, v. All comes from the Boltzmann distribution. I want to get some results out of that and connect it with something we've already known. Let me ask you a question. Does that probability work for a liquid, a gas, an ideal gas, solid, none of the above, all the above? How good is it? Have I made any restrictions? How many people think it's true for everything? Raise your hand. Not too many. You think so? How many think it's only true for ideal gases? Okay. How many think, so here's the answer, it's true for everything as long as it's not too low a temperature. So that is true for this piece of chalk. The particles in this chalk are vibrating around. They have a certain velocity. If you measured their speed distribution, it's given by that. Here's a glass of water. The molecules in that water, they have a speed distribution given by that. The gas molecules in this room, they have a speed distribution given by that. Hard to believe. It's all the same. The only time it breaks down is when you get to very low temperatures and you have to use quantum mechanics to get it. Because notice this formula here for the kinetic energy, that's a classical result. It doesn't work at very low temperatures. It doesn't work for quantum mechanics. It doesn't work for atoms, right? You know, like the electrons in an atom. It doesn't work for that. But other than that, it works fine. Even your own body, the particles in your body, is to the extent to which you can treat your body as being at a certain temperature, this will work. Okay? So now I'm going to do some calculations. I'm not going to actually do the calculations because they involve various integrals, but I'll give you the results. Probably the most important calculation is to look at what's called the root mean square average. And what this is the square root of the integral from 0 to infinity, P of v, v squared dv. All right? So it's the root mean square. That means we squared v squared, We found the average. That's the mean. This is the mean. This is the average, right? Because this is a probability. You multiply a probability by the thing you're averaging, and then you get the average. And then the root means take square root. All right? So if you do this, surprisingly, you get the following answer. 3 kt over m. And I'll actually write out what that is. About 1.73 times the square root of kt. I'm sure you all wanted to know that. Actually, you do want to know that. All right? Because if I square this, I get that VRMS average squared is equal to 3 kt over m. But what is the mean kinetic energy? So the mean kinetic energy is equal to 1/2 m, this VRMS average squared. Wow. So all I got to do is multiply this by 1/2 m, and lo and behold, I get 3/2 kt. We finally derived one of the key results that we've been using over and over and over again for ideal gases. Because for an ideal gas, you only have kinetic energy. So this is the result for the ideal gas, that the total energy for each particle is 3/2 kt, the average energy. And you multiply by n to get the total energy for all n particles. Think about that. That's also the total kinetic energy in this piece of chalk. It's the total kinetic energy in this little bit of water. It's the total kinetic energy in this air. It's the total kinetic energy in the floor. In your tables, it's all the same. It's just given by that. You just multiply that number by the number of particles, and you get the total kinetic energy. So the only difference between this piece of chalk and the air and the water is the potential energy. Now, there are a couple other averages you can get out of this. For instance, we could compute the average speed, right? The average speed. I can compute that. I just use the same thing as this, and I get the integral 0 to infinity p of v dv. And that gives me the square root of, you can look this up, 8 kt over pi m. And that turns out to equal 1.60 times the square root of kt over m. Remember, this m is the mass of the particle. Okay? So the average velocity, speed, is a little different than the root mean squared. All right? And then there's one other useful result, and that is what is the most probable speed you can have. Take a look at this. What's the most probable value for the x component of the velocity? What's the most probable value? Look at it. Tell me, what is it? What makes this as big as it could be? What makes this as big as it can be? What value of v sub x? You don't have to do any calculus. You can just look at it. What is it? What value of v sub x makes that the biggest it can be? Yell it out, somebody. I won't look. 0. 0. The most probable value is 0. The same for v sub y. The same for v sub z. So why aren't the particles not moving? That's the most probable value. Well, the answer is very similar to this issue here. There are not many cases like that. There are many more cases where you have non-zero components. So if we looked at, where's the sphere? If we looked at the little shell around 0, this shell is much smaller than that shell. Okay, so that's why the probability is not 0. So how do I find the best speed? What's the maximum speed? Well, that's pretty easy to do. This one I can actually do the calculation, but I won't bother. All right, so to find the most probable speed, what do you think I do? Here's my P of V. What do I do to get the most probable speed? The place where P of V is a maximum. This involves calculus. What did you learn in calculus? How do you find the maximum or a minimum of a function? You differentiate, and what do you do with that derivative? Set it to 0. Very good. So all you got to do is take dp of v, dv, and set it equal to 0. You do the calculation, you get v. This is the most probable, and it turns out to be the square root of 2kt over m. And that equals about 1.41 times the square root of kt. Okay, so if we plotted p of v versus v, we would get something that would look like this, some function, and this value here would be v most probable. But the average v and the root mean square would be a little bit bigger. And the reason for that is there's just more area under the curve out here. This part of the curve is restricted because you can't get smaller than 0. You can't have a speed that's negative. The speed is 0 or above. So we've really made a connection here between what we did before and now. Think about it. The time when I told you that the energy was 3/2 nkt, that's like the translational energy, kinetic energy for the ideal gas, I kind of pulled the wool over your eyes. In kinetic theory, I said, well, we'll just define the temperature that way. That's the best you could do. All right? Otherwise, I said, well, you do a bunch of experiments, which none of you have done. So that's not that convincing. But here I derived it. I derived it, and I figured it out. That's the power of statistical mechanics. Statistical mechanics is frequently used as the paradigm for a lot of physics. Namely, we have things that occur at one scale, and we explain it at a smaller scale. Okay, so statistical mechanics is a perfect example of what's called reductionism, reducing thermodynamics to microscopic physics. And if you took a real stat mech course, you would actually use quantum mechanics so that we could derive even more results and what happens at low temperatures. All right. Now, in order to see how this works, we're going to do a problem. So the problem I'm giving you is one that is probably rarely seen by students in introductory physics. But I figure you guys are smart. You should be able to do it. All right, so here's the situation. We're going to talk about what's called a two-level system in a heat bath, temperature T. All right? So we have a system. You can think of it like before, like a molecule, for instance. But it could be a whole system. And it turns out this is actually a pretty useful model for some real situations, usually for some molecule. All right? 2 levels means there's just 2 energies. We'll call one energy the ground state 0. This is called the ground state. And the other energy, E1, is called the excited state. Simple enough. This is the simplest problem you can do in statistical mechanics. An example of a 2-level system is an electron in a magnetic field. The electron can either point along the magnetic field or opposite. Due to quantum mechanics, it can't point any other way. I mean, it sort of does, but it doesn't really. There are only 2 states. That's the important point. All right? So when you learn about quantum mechanics, you'll learn about this. All right, so there are a bunch of questions. The first question is, and you may be surprised, what is Z? What is Z equal to? Is Z up there? No. We had to get rid of it. Any ideas? What's Z? There's only 2 states. Remember, Z is a sum over all the microstates. There are 2 microstates. One has energy E0, the other one has energy, which equals 0, and the other one has energy E1. So what is Z? Z equals the sum over all the microstates, e to the minus e sub I over kt. All right, so what does that equal? How many terms are there? 2. Can you figure out what they are? So Z is equal to 1 plus e to the minus E1 over kt. Why is it 1? Because e to 0 is 1. What is the probability of being in the ground state? So what's the probability of being in the ground state? So that's called P0. What is it? Use that Boltzmann distribution. All right, so what does the Boltzmann say? It says e to the minus E0 over kt divided by z. All right, so what's that equal to? It's just 1 over that, 1 over z, E1 over kt. And what is the probability of being in the excited state? Call that P1. Well, that's just e to the minus E1 over kt over 1 plus e to the minus. We get that. What's the sum? P0, what is P0 plus P1 equal? 1. That's good. Because if you sum up all the probabilities, and there's only 2 possibilities, you got to get 1. Let's compute the average energy of the system. How the hell you do that? So here's something from probability theory you may or may not know, or you may not know it in this way. To get the average of anything, you take that thing, multiply it by a probability, and then sum over all the possibilities. So this is just equal to E sub I, P sub I. So we sum up over all the i's. Well, in this case, we only have 2 cases. So we have 0 times P0 plus E1 times P1. That's all there is. All right? E0 is 0, which is why I chose it to be 0. And E1 is E1. All right? So I can write that down. And what do I get? That's 0, E1 times P1. I get E1, e to the minus E1 over kt divided by 1 plus e to minus E1 over kt. All right, great. All right, so what? All right. I'm going to want to look at what happens to the energy at high and low temperatures, and I also want to look at the heat capacity, which means taking a derivative of that. So I want to simplify this. So the way you simplify it is you try to get rid of, since I'm going to take a derivative with respect to t, I want to put that, have as few places as possible with t. So this is just equal to E1 times e to the E1 over kt plus 1. What did I do? I just multiplied top and bottom by e to the plus E1 over kt. So I canceled this, gave me a plus there, canceled this, gave me 1. So that's the average energy. Now I want you to take the derivative of that with respect to temperature. Let's rewrite E1 average, E average, as E1 as 1 plus, I'll write it the way, e to E1 over kt plus 1 to the minus 1 power. All right, so let's take the derivative of this. So C, the heat capacity, is dE1, E average, dt. This E1 just sits there. So I take the derivative of this. I have a minus 1 here, so I have minus 1, and then times this thing, E1 over kt plus 1 to the minus 2 power. Everybody agree with that? And then what do? I have to take the derivative of what's inside. What's the derivative of an exponential? Well, it's equal to itself times the derivative of this. Ugh. And that's E1 over k t squared and a minus sign. All right. I did it. Now I'm going to write this in a funny way. Notice E1 times E1. So I have E1. And notice I have kt squared. I'm going to write it as kt, and I'm going to square it. But that's not quite right, because I only have one k here, not two k's. So I'm going to multiply by k to fix that. All I have left is e to the E1 over kt divided by e to the E1 over kt plus 1 squared. OK, great. So now I have the heat capacity, and I have the average energy. Let's see what happens at high and low temperatures. So high T, that means E1 over kt goes to 0. It goes to 0. So let's see what E bar goes to. So that implies E bar, which equals E1 over e to the e over kt plus 1. And what does that go to? It just goes E1 over 2. Whoa. Now, if I asked you this before we did this calculation, which I should have done, most of you would have said the energy was E1 at t equals infinity. Not true. The system does not go to the highest temperature state at t equals infinity. Not true. What does t equals infinity mean? It means every state is equally likely. Every state is equally likely. So like, imagine this room, and there was a fire drill, and you're all running all over the place. Completely random. Where you are is completely random. Every state is equally likely, because you're all not paying attention, you're just running around randomly. Right? That's what t equals infinity means. All right? It's like a riot. Okay? Same thing for particles. So every state is equally likely. You do not go to the highest energy state. So notice this is equal to E0 plus E1 over 2, because E0 equals 0, right? Okay, so to get the average energy at t equals infinity, all you got to do is average all possible energies. What about the heat capacity? What happens to C at t equals infinity? heat capacity. What happens as T goes to infinity? What does C do? It's 0. Wow. It actually fits the third law of thermodynamics. Because only in the third law, we know the entropy goes to 0, and that means the heat capacity has to go to 0 too. And why does it go to 0? Well, this goes to 1, this goes to 2 squared, but this goes to 0. 1 over infinity is 0. That's fantastic. Notice the ideal gas doesn't do that. All right, so we have the first example of a realistic model at T equals 0. It's the first example we've had. The ideal gas is no good at low temperatures. What do you think is going to happen at T going to 0? Somebody, you should be looking at me with strange faces because I made a mistake. I started talking about T equals 0. We're at T equals infinity. So everything I just said in the last minute or two is wrong. Has nothing to do with the third law. But it is different than the ideal gas. Why? Why is it different? Why do you think the heat capacity goes to 0 at T equals infinity? For the ideal gas, which is a perfectly good model, at high temperatures, the heat capacity goes to a constant. You know, if you have a monotonic gas, it's 3/2 NK. That's it. Does not go to 0. It's a constant. But here it goes to 0. Why? So why does the heat capacity go to 0 at T equals infinity? What's different between this and the ideal gas? Let me ask you a question. How many microstates are there at T equals infinity? How many possible microstates in this system are there at T equals infinity? 2. There's only 2. How about for the ideal gas? How many are there? There are billions and billions and billions. There are a huge number of microstates. There's so much energy around, T equals infinity, there are a huge number of microstates. So when I add energy to the system, I can keep increasing the temperature. I can keep getting it going up and up because there's no limit. The only real limit is special relativity, not quantum mechanics. Special relativity, because particles can't go faster than the speed of light. So once you get really high, something's got to give. Okay, so the reason the heat capacity does not go to 0 for the ideal gas is that there's no limit on the number of microstates. There's no limit on how much energy you can add to the system. Here, you're limited. That's the total energy. You can't get any bigger than that. You're stuck. And because you're limited, the heat capacity's got to go to 0. Because I can add more energy to the system. The average energy is already the average. It can't get any more average. Right? That's it. Okay, now let's go to low T. Low T. And what this means is E1 over KT goes to infinity. So what happens to the average E? Right? So what happens to the average E? It's 0. It goes to the ground state. And that's what you expect. At T equals 0, the system will go to its ground state. It'll go to the lowest energy state. All right, very good. What happens to the heat capacity? That's a little trickier. Here's our formula. What happens? What happens to this term here? What happens to the numerator? What happens to the numerator at T equals 0? Get large or small? Very large. What about the new denominator? Large. Is the denominator larger than the numerator? Yeah, because we have a 2 there. All right, so this thing will go to 1 over e to the E1 over kT. Right? That's what this whole thing will go to. And as kT goes to 0, this goes exponentially. 1 over this goes exponentially to 0. All right, that's fine. What about this guy? As t goes to 0, what happens to this? Big. So you have a big number times a very tiny number. Which one wins? The exponential. Why? Any ideas? You could work this out. You could look it out on your calculator, try a few numbers. But here's the bottom line. Exponentials, we say, will always kill any power of t. If you have e to the minus x times x to n, this always goes to 0 as x goes to infinity. This goes to 0 much faster than this goes to infinity, no matter what n is. N can be 5, it can be 20, it can be anything. Try it out on your calculator, and you'll see. Of course, your calculator will probably poop out at some value of x. All right, so c goes to 0. Do you remember everything I said before that was wrong? Now it's right. The heat capacity goes to 0 at t equals 0. That's an example of the third law of thermodynamics. It goes to 0. The reason it goes to 0 is the following. We have a two-level system. Here's E0, E1. If I'm at low enough temperature, if E1 minus E0 is much, much less than KT, right, then when I add a little energy to the system, I can't get up to E1. I just can't. Okay, so delta E over delta T will be 0. So as long as delta T is much, much smaller than the gap between the first excited state and the ground state, the heat capacity will be 0. And that's going to be the case for all systems. All systems are quantum mechanical as you go towards t equals 0. And except for some really bizarre cases, the ground state and the excited state is a finite energy. There's a discrete energy between the excited state and the ground state. All right. So the last thing you could do is plot E versus T and C versus T. So E starts out at 0, ends up something like that. And this is E1 over 2. And then the heat capacity starts out at 0. There's some peak, goes like that. All right? And this value here will be something like E1 over T, proportional to E1 over T. So the heat capacity has some peak in the middle. That comes from the fundamental law of calculus. If a function is 0 at one spot, 0 at the other, and non-zero in between, there better be a maximum somewhere, or it could be a minimum, but the heat capacity is always positive, so it's got to be a maximum. All right. Okay. Make sure you understand this.